Students, I'm going to tell you about the boundary conditions for E, D, B, and H in electromagnetic theory. So for that, we'll have a small introduction of the previous things which we know, like how E and D are related and how B and H are related to each other. So look at this document. So look at this value here. So you can see the value D is equal to epsilon naught E plus P. So you know the values. D is displacement, electric displacement, E electric field, and then P is the polarization value. And then this can be turned like this, epsilon naught plus psi E, and totally it's becoming epsilon E. Instead of epsilon naught, it becomes epsilon when it goes through a medium. So hence the relation is D is equal to epsilon E. Also, you can see the relations here. E is equal to 1 by epsilon naught D minus P. So all these relations you might have seen in your BSc, the relation between EDP. So the same thing it is shown here. You can also see the integrals, Gauss law in electrostatics, with integral epsilon naught E dot dA is equal to integral D dot dA is equal to Q, where A will be the area of the medium through which this electric field is passing. Then you have the Q as the charge enclosed. You can also see how the dielectric constant is. See, these are the symbols. You can see E, P, D, B, M, H. What do they represent and what are the units of that? I shall share all this material with you after the class. And you can see the relationship between B and H here. Look at this integration 1 by mu naught B dot dl is equal to integration H dot dl, or you can say 1 by mu naught B is equal to H. H is equal to B by mu, or H is equal to 1 by mu naught B minus M, where M is the magnetization of the medium, or B is equal to mu naught 1 plus psi M H. And also mu is equal to mu naught 1 plus psi m. So these are the basic relations which we must know before deriving the relationship between E, B, D, and H. And now we'll come back to our presentation or the topic today, which I told you. We'll derive these relationships in a medium where we use the term called as boundary condition, and we have a new term called as interface. So let us see what is that interface and how you can deal with that. Please look at the screen. This is the topic which we are going to learn. We have the applications of electromagnetic waves, several applications, and one among that is reflection and refraction. So this happens when electromagnetic wave is trying to travel through a medium into another medium. So reflection happens at the interface into the same medium, and refraction happens after the interface into another medium. So the outcomes of this lesson are, by the end of this lesson, you will be able to learn about the discontinuities in a medium. derive expressions for electric and magnetic fields at the discontinuities, derive the boundary conditions for E, D, B, and H. Boundary conditions at the surface of discontinuity. So what is that? How does it look? And how can we assess? So in a homogeneous media, electromagnetic quantities vary smoothly and continuously. So what is the term vary means? It means change. So the electromagnetic terms which we were speaking about, E, D, B, and H, they change smoothly and also continuously in a homogeneous media. But we are talking about interface, a new term called as interface. At an interface between dissimilar media, it is possible for electromagnetic quantities to be discontinuous. These discontinuities can be described mathematically as boundary conditions. So yesterday, while I was talking about, I told you about guided waves. So boundary conditions talk about the guided waves. Electromagnetic waves are not free to move as they like. They are bound to certain conditions because of the medium. So they used to find solutions for the associated electromagnetic quantities. So look at this figure. This is what I was speaking about. We have the incident ray here, which is having the wave vector ki, and then we have the reflected ray kr. The angle is same here, theta I and theta I, because the angle of incidence is equal to angle of reflection according to law of reflection. And then you can see here n1 is a medium with refractive index n1, and here there is medium 2 with a refractive index n2. So both the medias are different. There is dissimilarity. And then you have this line which we call it as interface. So at the interface, what's happening? The light is getting reflected into the same medium, and also the light is getting refracted into another medium. So the angle of refraction, which we also call it as the transmission, angle of transmission, theta t, and the wave vector for this transmitted light is kt. So this is the depiction of two media with an interface and electromagnetic wave taking two components, reflection and transmission. Now, so to derive this relationship between B, D, and H, we have one small diagram which is very informative. Please look at this carefully. The previous figure I showed you, there was medium 1 and medium 2 with two different refractive indices. Now here at the interface, so this dark line above here is the interface between two media, medium 1 and medium 2. Here we are trying to draw a surface. It's like a box. It's not just ordinary surface, but we are trying to draw a surface like a box, which has four surfaces, as you can see here, S1 and then S2, S1 on the top, S2 on the bottom, and then the side of this box or the cylinder, we are considering it as S3 in medium 1 and S4 in medium 2. So this surface is split into half. Whereas the cross-section area of this surface is capital A. The height of this box is small h, and then n is directed like this. N1 is towards this side and N2 is towards this side. So this is the primary idea, like how we are going to approach with the derivation of B, D, E, and H. Okay, let us see. Now, As we always take the Maxwell's first equation. Divergence D is equal to rho. If we take volume integral V over the entire volume of the surface, which I have shown you already, the integration of that is equal to this. And then, because this is a volume integral, to convert it into a surface integral, I can use the Gauss divergence theorem for this above equation, for equation 2. And then, using that Gauss divergence theorem, I get this equation. Integration S d dot ds is equal to integration V rho dV. But here, there is one small trick which we apply, the surface. So the integral over the entire surface I said, but the surface was divided into 4 parts, S1, S2, S3 and S4. Just go back to the figure, you will understand how we have divided it. So this integral d dot ds is divided as integration s1 d1 n1 ds, because near s1 n was n1, and then at s2 n was n2, and then near s3 I consider the unit vector as n1 prime, and near s4 I consider the unit vector as n2 prime. So these are the same electric displacement and the unit vectors, but because they are related to a different surface, we have taken the different notations. But these 4 parts, they represent the same. But look at the third term and the fourth term. Both these terms refer to the side of the wall of the box. They are not the top, they are not the top and bottom, but they are the side of the box. So please remember that. Now, you know the height of the figure, in height of the box in the figure, it was small h. If we consider h is being shrunk, I mean, you take the box and then you start pressing it, you shrink it. The height is reducing slowly, 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 slowly. And then there is a limit, like you are approaching to 0. So in the limit where h is approaching 0, the third and fourth terms vanish. Why? Because they are the sides of the wall, and when you are shrinking the box like this, there is no side. So the third and fourth terms in equation 3, they just vanish, and S1 approaches S geometrically, and the entire surface takes the form as shown in the figure, where you have a value like A. So there was a disk like A. So the entire surface is just pressed like this, it is shrunk, and then you have a small surface A instead of having the entire volume S. So then the equation 3 is changing like this. You can see under limit h approaching 0, integration S. Instead of S1, it has become S. S2 also has become S, because there is no extra surface right now. It's a thin area like capital A. So we are taking S here, we are taking S here, and then on this side also we are applying the same limit. H tends to 0, integration V rho dV. And then how do you write it in terms of surface charge density? Because there is a surface now, you don't say that there is no surface, there is no volume, but there is a surface, and that surface, if I take the surface charge density and I want to represent these equations in terms of that, then I can write the equations like this. So d1 n1 s1 plus d2 n2 s2 is equal to sigma a, and then because s1 and s2 are approaching to s, the same value, and then that s has become a, capital A, which is a thin slice which we have mentioned. So this is equal to like this. So because the area is just arbitrary, we don't know, we did not define the area like how many square units it should be, and then n1 is equal to n, or n2 is equal to minus n. So what do we get? We get d1n and d2n are the normal components of electric displacement vector in the two media. So replacing n1 is equal to n and replacing n2 is equal to minus n, what do we get? d1n minus d2n is equal to sigma d1n. This is just a representation, d1 dot n. I'm representing it as d1n, and d2 dot n, it is represented as d2n. So you can see d1n minus d2n is not equal to 0 here. There is a value. If I got 0 here, then I would say it is continuous. There was no change in the component of D. But here D1n minus D2n is equal to sigma. So there is a value. It means D component or the electric displacement is not continuous at the interface, but it is changing by an amount equal to the free surface charge density of at the interface. Means near the interface, if you have some charge, then the continuity is changing with respect to the value of the charge. So this is what it depicts. Now I'll explain in the same way how we can derive the values for B. I mean, let us see whether B is continuous or discontinuous at the interface. Now look at this. The same equation, we'll use the same Maxwell's second equation. There we used Maxwell's first equation because it was divergence D is equal to rho. We needed D, but here we need B. That's why we are using divergence B is equal to 0. Then we take the volume integral over the entire volume of the box, which was shown in the figure, the same diagram which I showed you. So you take the integral over the entire volume, then divergence B dV is equal to 0. We use the same Gauss divergence theorem to change volume integral to surface integral. We get integration B dot ds is equal to 0. So there what we did, we divided D into 4 components with respect to the surface. So we'll do the same thing here. We'll divide B into 4 components with respect to surface S1, S2, S3, S4. The same thing here, S1, S2, S3 and S4 as we did in D. So what's happening to that? As you know, when H is approaching 0, the same thing, S3 and S4 will vanish. We have only S1 and S2. We'll apply the same limit. When H is approaching 0, the above equation takes the form integration A. Why? Because the surface S1 and S2 is going towards S, and S is now become the area of cross section capital A. So hence the integral looks like this, integration A, B1 dot N1 plus B2 dot N2 is equal to 0. Also, you know that the surface is arbitrary. Hence, what we can do, we can remove the integral and then take the values like this, B1 N1 plus B2 N2 is equal to 0. And then N1 and N2 are both in opposite directions. So therefore, if N1 is equal to small n, then N2 will become minus n because of the directions. Hence, what we can do, change equation 9 like this. B1 dot n minus B2 dot n is equal to 0. Or B1n is equal to B2n. Hence, the normal component of magnetic induction is continuous across the interface. How do you say continuous or discontinuous? Because B in the first medium is equal to B in the second medium. It did not change. So when I try to find out the change in B, it is 0. There's nothing. But whereas in D, when I took D1 minus D2, the value was sigma. So there was a change. So hence we said D is discontinuous, whereas across the interface, B is continuous. It is the same. There is no variation. There is no change. So this is what we derive about D and B. And then what are left? E and H.